Thank you, everyone. Today I'll be talking about multi-calibration, what it is, how you can use it in kind of real-life machine learning settings, and how you can use MCGrad, which is the Python library that we developed for multi-calibration. This collaboration between my team at Meta, we've been working on developing this for like the past 2 years, both on the research side as well as implementing the open source tool and bring this, helping many teams with machine learning engineers across Meta to kind of use this in production systems. And a collaboration with London School of Economics, with Milan Varsnovic, who's full-time, who is professor in statistics at LSE and part-time researcher also in our team. So first slide about our team. So we're Central Applied Science. So we're a team basically of applied scientists who do research that's kind of inspired by real-world problems. So we basically collaborate with teams and machine learning engineers from across the company, teams from integrity, teams who work on ads, on ad auctions, teams who work on feed ranking and all kind of practical problems like that. And we try to kind of help them, but from a more academic perspective. So we collaborate with them, we help them develop new machine learning algorithms. We publish papers about that, and ultimately we collaborate with machine learning engineers to get these methods used in production. And yeah, we're quite a multidisciplinary team. So we do statistics and AI, machine learning, but we also have people with other backgrounds like economics, computational social science, operation research. One thing that our team does a lot is basically build platforms and tools. Often those are tools and platforms that kind of fill a need or fill a gap that a lot of machine learning engineers in the company have. For example, this MCGrad that I will be talking about today. But we've also built platforms like an active learning system, which teams that use kind of human data collection can use to kind of make these kind of processes more efficient. So that's a little bit about our team. The rest of the session, I'll first talk a bit about, just walk through a couple of examples of like applications of machine learning at web scale, like at in how ML is integrated in kind of user-facing products. And then we'll move on to what multi-calibration actually is and how this actually connects, like how is it relevant and how is it useful and needed kind of in this machine learning production systems that are kind of used live. We'll also look, so that's a bit on the application side, then we'll move a bit into metrics, like how do we even measure, like we'll talk about what multi-calibration is, but how do we measure whether we actually achieved it, and how do we achieve it, like how can we achieve multi-calibration, so that's a bit on the algorithm side. These connect to also 3 different papers that we published. So we have a paper here on the application side of multi-calibration that we just that just got accepted at ICML, and the 4th one, the algorithms paper, we just got accepted at KDD. We presented it there in the summer. We'll try to keep this also hands-on and as like in tutorial format. So what we have is a Google Colab notebook. I have a link here at the bottom, but it's quite long, so you probably don't want to type all that. There's also a tutorials page, which is mcgrad.dev /docs/tutorials. And if you go there, then the same tutorial can be opened here through this link. So that's mcgrad.dev /docs/tutorials. And the rest of this session, I'll basically be going back and forth between some slides, explaining some things on slides, and every now and then jumping back to the tutorial and running part of that and kind of walking you through. I'll open this myself as well. It's just I'll to copy only the link. All right, just run the first. Is anyone getting this part to run? I'll just take a short break here to see that. So the first few sites just basically install the package, the MCGrad package, and then do some basic imports, and then it does some data loading. If you want to follow along this tutorial with your own data set rather than the one that we've kind of preloaded here, you just want to see what it does on your data, then feel free to kind of swap it out and kind of follow along with that. For now, I'm just going to run the data loading cells and then hop back over to the slides, and we'll get back to the tutorial later. Is this part working for everyone? Yeah? Perfect. All right. So yeah, a couple of applications of machine learning in user-facing systems. So one obvious example is like a recommender system. For example, in Facebook, we may want to kind of rank posts for users who load the website, and we may want to optimize for different criteria here, right? So maybe we want to optimize for different ways that users can engage with this content. So maybe we want to, in some cases, account for do they actually click on the content. In some cases, maybe it's content that's kind of maybe you can purchase it. So maybe there's like so it's maybe another objective. Maybe we don't want people to kind of, if people unfollow a group, unfollow some particular group that the content is from, maybe that's a sign that they actually didn't like it. So we may have like different objectives, and very often how these kind of ranking tasks are actually done is you actually use a combination of like different machine learning models that each model these different mechanisms. So like you may model the probability of a click, you may model this probability of an unfollow, probability of a purchase, and maybe we'll ultimately have some idea of how these different terms kind of correspond to what we actually want to optimize for in terms of business objective, and that often leads to some kind of simply like some linear weighted combination of these terms. So this is a very simple way in how you can kind of design a recommender system. I'll later get back to how this connects to multicalibration in this weighted, this simple kind of linear weighted kind of combination of models. Another kind of common real-world system where machine learning models play a role is in ad auctions. So you may have a system where advertisers can bid, and ultimately you want to show ads to users. And advertisers may bid a certain amount of money for a conversion, or for a click, or for whatever kind of type of event they're kind of willing to pay for. And ultimately, you want to estimate which potential ad impression might kind of lead to the highest amount of revenue. So you want to know which one should we show. well, this is ultimately like, you may have an advertiser bidding like $2 for a click, or another one bidding $10 for a purchase. So ultimately, to know which one wins the ad auction, you don't just need to know how much they bid. You also need to know what is actually the probability of this event actually happening. So what's the probability of a click, or the probability of a purchase, or whatever it is that the advertiser was kind of bidding to pay for. So this is another kind of system where ML models here obviously play a big role. Then we have like another kind of big category of kind of machine learning applications are like in integrity. So you may have, for example, transactions, and maybe some of them could potentially be fraudulent or not. You don't really know, but you try to estimate that for all of them. And maybe you have some team of kind of manual investigators, or maybe you're kind of able to take an action like blocking a transaction if you believe it's fraudulent. And in such systems, it's pretty common that basically you just have like a threshold-based application. Like you just put a threshold and you say, okay, if the probability of kind of this, if the probability of fraud here is kind of above a certain kind of fixed level, then we may take an action like either block this or send it to an investigator. Or so we have seen 3 kind of different applications of machine learning systems used in production settings, but they all have kind of different, I think the main point here is that these are not just different application domains, these are also different ways of how the outputs of the machine learning models are actually simply used. So here, it's just comparing the output of the machine learning model simply with a threshold, right? Here, in the ad auction was a little bit more complicated, because here here it's a system where an application where you multiply the output of the machine learning model with something else, and then you do some sort of sorting based on that. And here in the recommender system case, we were actually at 3 different machine learning models, and then some kind of weighing on top of that, and some sorting based on that. So these are kind of the distinguishing factor here is what matters ultimately is the decisioning mechanism and the application, and the ML model is just a component of that. And what we want to optimize is actually the application that is integrated in, rather than simply the machine learning model in itself. So how do we typically look at ML models? Well, typically we evaluate simply ML like performance metrics. So we may look at the likelihood, we may look at precision, recall, metrics like that. So what else should we potentially look at? By the way, I didn't tell you before, but if there's any question you have at any point, feel free to don't have to wait at the end, just kind of interrupt whenever you feel, whenever you have a question. So there's also a notion of calibration, which is, for example, here we may draw a curve of like, okay, what is the predicted probability? We may put that on the x-axis. And we may make different buckets of those. So for like wherever the prediction was kind of low, we may actually compare that with like, okay, what's the average of the label there? So whenever we estimated like something like 0 to 25 here, what's on that group? What's actually the mean of the outcome? If you would assume that for a calibrated model, this should be also like around 0 to 25. So if we have here the 0 to 25 point, it should line up with like also 0 to 25 basically on the labels. So that's kind of the predicted probability then should line up with the empirical probability. And if that would give you a line that if it's perfect on this plot, you would be perfectly on this kind of blue line. So you may have a model that looks like this red one. That's an example of a miscalibrated model. So here what we see is like whenever you predicted something low, actually the truth was even lower. And whenever you predicted something high, actually the truth was actually even higher, even closer to 1. Right? So this is kind of an overconfident model. It's overconfident on both sides. And a perfectly calibrated model would look like this, right? Is this concept clear? So this is calibration. There's exist lots of techniques to kind of ensure that your model becomes calibrated and to measure whether you are. We'll go a little bit into some of those later. But the question is, okay, is this enough? Like if we're calibrated, like what do we have then? So actually, it can still be the case that if you look at all your predictions, and you kind of generate this calibration curve, that it nicely looks like this. So it looks like you're calibrated. But now it may be, if you look into subgroups, you may still be miscalibrated in particular subgroups. So here, for example, you may have an example where, okay, all your data looks like, if you calibrate the calibration curve, it looks nicely like this. It's the red line. But actually, if you split it out between all the data in the US and all the data outside of the US, you actually get a curve like this and a curve like this, and kind of combined, they nicely cancel out, so it looks like this. But actually in subgroups, you see that we are not calibrated here. So now the question is, I think 3 questions here. Does this really matter? And can we measure whether we are calibrated also in subgroups? And can we achieve it? Can we actually do apply some sort of algorithm or procedure such that after this we're like perfectly calibrated in subgroups? That would be great. I have some boring mathematical formula on top. Let's skip that. So let's go back to the 3 applications that we had. So we had the recommender system, the ad auction, the integrity system. So what do we actually get if we are kind of not calibrated in? Well, so let's reason a bit through about what happens if we're not calibrated in these subgroups while we are actually running kind of a application system like this. Okay, so let's assume that, for example, this p-click model, right, the machine learning model where we're estimating clicks with, let's say that it has a calibration curve that looks like this, right? So the US, like users in the US, maybe we're kind of underestimating the probability of click. So because of whenever we thought that the probability of click was like 0.5, actually it was more like 0.6, 0.7, roughly. So we're underestimating it everywhere. Maybe the degree to which we're underestimating it depends a little bit on the probability. We're not consistently underestimating it by the same factor, but we are underestimating it. Well, outside of the US, it seems like we're overestimating the probability of click, right? So if we have this kind of bias in our model, what happens is that, okay, if we were applying a machine learning model like this and we were computing all these probabilities for our users, we were basically computing all these probabilities and then we were weighing content like this. So what happens is, if we had a particular weighing factor that we believe to be the correct one, that we wanted to have, in some sense, if we were underestimating the clicks in the US, we were overestimating it outside of the US, then basically it's kind of like we were applying too low weighing factor in the US compared to what we wanted to have, and a too high one outside of the US, right? So we're not getting the trade-off that we wanted. So this means that actually, if you're multi-calibrated, then you're actually not applying you're not consistent in applying kind of the optimization criteria that you really wanted to optimize for. This can really hurt kind of the performance of the system, even though in the machine learning models metrics, if you would compute like cross-entropy loss or whatever in each model individually, it might look okay. It's just not on the whole system level, doesn't look okay. Same thing in ad auctions, right? So if you're kind of underestimating the probability of conversion for some groups of ads, you're overestimating it for some other groups of ads, then ultimately you're kind of wrong in deciding what the winner of the ad auction is. So you're kind of not making as much revenue as you could have been making. And then there's the example of integrity. So what happens if you're just applying this threshold? Okay, so what if you're applying the threshold of like 0.8 to all our predictions, right? And above that, you take a particular action, like blocking a transaction or blocking a, or kind of investigating it. Okay, so what happens now is like, okay, you take you take an action whether you're like above here, basically, right? So that basically means that outside of the US, we're taking an action when the actual probability of fraud is like 0.6, while in the US, we take only an action when the real probability of fraud is like, I don't know, 0.9 or something, right? So we're really inconsistent in when we're taking an action on this transaction. And this can really lead to situations where if the investigators, basically, if you calculate the precision of the set that you have actually decided to take an action on, it can look good on the whole set, but it can become arbitrarily low in particular markets. So this can really become an issue. So this is basically 3 examples. We basically took a bit of a more like theoretical approach and kind of generalized all of this kind of thoughts a little bit into one kind of set of theory, which is this paper with the name Multicalibration Yields Better Matchings, which we just got accepted at ICML. It's a collaboration with a research group at Sapienza, University of Rome. Here we formulated the problem in the following kind of way. So this is a kind of, if you think about it, it's like a best arm selection problem, right? So this is like typical known kind of theoretical model in machine learning research. So we have like a slot machine with n arms, and we want to kind of, and you can think about this like pulling the arm is like taking an action. So it could be like investigating a transaction for fraud, or the other arm that you can pull is like not investigating an action for fraud, right? So each of these 3 settings that we just talked about, they can be kind of mapped back to this kind of theoretical model. And now the question is, okay, so we have this slot machine with n arms, and we have a best arm selection problem. So we want to know which arm to pull, right? Which action to take. So here, it's known that if you have this kind of best arm selection problem, and you have known rewards. So for each arm of the slot machine, you know what is the reward, like in kind of reinforcement learning sense, basically. You know what is the reward of pulling that arm. Then it's very simple. The best action you can take is just take the argmax. Take the arm that maximizes the reward, right? That's simple. So that's known rewards. But then you have the setting with stochastic rewards, but still known, right? So now, pulling an arm you may not know of, it may give you some reward taken out of some kind of distribution, but it's still a known distribution. In that case, there are theoretical results that say, actually the argmax is still the best. Just take the argmax of kind of the expectation of that distribution. You know that this is kind of still the base optimal policy. So there's theoretical results on that. But now, actually in real life, the distribution is not known, right? We have no idea. We can only kind of try to model it and estimate it from the data that we have. So what do? Typically what we do is we just use a machine learning model to predict the rewards, right? And then we apply the argmax. That's typically how we do. So going back to just take the integrity setting, we estimate how we estimate kind of the consequence of investigating this transaction for fraud and not investigating that transaction for fraud, and we just do whatever we think kind of is better. But actually, if you look at if you study this best arm selection problem, and you have estimated rewards rather than known rewards, and then actually the policy of just taking the argmax no longer has the same guarantees. Is no longer base optimal like with this known reward setting. And it's you don't even have a guarantee of having asymptotic optimality. So then the question is like, okay, everything breaks down if we're estimating rewards rather than knowing them. So we were wondering here, like, actually, can we perform can we get a policy that's as simple as just taking the argmax, right? We just want to have a really simple policy when we apply something in production. We just want to take the action that we think is best. Can we keep a policy that's so simple and still take optimal actions? And what we actually prove in this paper is you get that. If your model F that you use for kind of estimating these rewards, so that's this model here, this model that predicts the rewards. If that model is multi-calibrated, only then and only then the argmax policy of selecting your decision, selecting your arm, gives you base optimality. So this is nice because now it seems like all these kind of 3 different decision systems that we've seen in the beginning, if we just could have these estimated probabilities multi-calibrated, then selecting the actions we should take becomes easy in all of those. So yeah, this result, it's kind of abstract in general, but it applies to recommender systems, it applies to ad auctions, to financial fraud, and so forth. Any questions so far? All right, metrics. I have a few slides on how we can actually measure multi-calibration. And then after these few slides, we go back to the notebook because we have a couple of cells and a couple of plots there on measuring multi-calibration as well. So why do we need measurement? Well, it's nice that we have this theoretical property of multi-calibration, and we've seen that it's important in machine learning production systems. But in practice, we all know that ML practice is really driven by metric optimization, right? We all, most ML practitioners, their job is just basically taking a metric to goal on and kind of trying all sorts of things to improve it. So in order to be able to say whether we achieve multi-calibration, in order to optimize it, we first need also a metric to kind of say whether we achieved it and to kind of start improving it. So this is a paper. We submitted this to some statistics journal with the title Measuring Multi-Calibration, and it's a collaboration with the FAIR team at Meta. And there we came up with a metric that's called the multi-calibration error, which basically is, well, it basically has 2 steps. You have your data set. Like, first of it is basically you extract a whole bunch of segments. So you may say, I may have a gender in the data set, and you may say, okay, maybe time of day, maybe whatever kind of features you have in your data set. You try to kind of slice them in particular data slices in some kind of segment extractions approach. And then on the second step, you can measure the simply measure the calibration error in each of them. So basically, to design a metric for multi-calibration error, you basically need to come up with some way to do this, and you need to come up with some way to do this. And then actually, there's a third step. It's like, okay, what if we have like a whole set of calibration error measurements? So we have like a calibration error measured on each kind of group that we decided to extract there. How do we kind of get a single metric out of that, right? Because here you just get a set of calibration errors. We kind of ultimately want one metric. So there's 3 steps. We need to make groups, we need to measure miscalibration on each groups, and then we need to kind of aggregate that to a single number. So how do we do these steps? The first one is, well, to be honest, it's pretty naive at the moment what we're doing here. It's very simple. We just we just basically make the Cartesian product up to a particular depth, up to a particular size. So you may have like a large number of features, but we basically just take groups of like a subset of features, we can basically brute force this if we take all subsets of a particular size, and then for each of those, we basically make one group for each combination of values. So you may have like a feature like country, you may have like a feature like device type, like whether someone uses an iPhone or Android. So then we may generate subsets like, I don't know, iPhone users in France, Android users in the UK, and so forth, and basically the whole set of all the combinations of those. So that's pretty brute force. Maybe hopefully we'll come up with something better here, but this is kind of just the first step. Then then for each of those, you basically need to measure miscalibration. There is a metric that's very often used in calibration measuring calibration, which is called the expected calibration error. What expected calibration error does is basically, if these are your outputs of the model, then it just kind of bins the scores into groups of equal size. So here you may have like, I don't know, 0 to 0.5, and then you may have 0.5 until, of 0 to 0.05, then you may have 0 to 0.5 to 0.1, then you may have 0.1 to 0.15, and steps like this. And for each of these kind of buckets, on your test set, you calculate the average of your label, and that gives you like some number of like, okay, what was actually what on this group, what actually should have been on average the correct prediction, and you can basically check, okay, what's the difference of the average of the label and the average of the prediction in this group. So this is very often used. I think it's the most common metric in measuring calibration. There's actually quite some research on that. This is probably not the best metric to use. So one issue with this metric is that if you just change the binning scheme, right? So you change the method of like making these groups a tiny bit, then the metric is really sensitive to that. So you may get very widely different kind of calibration errors just by only changing your grouping procedure a little bit. So that's not very desirable. There's this paper here that kind of describes these kind of issues in more detail. And together with some researchers from FAIR, there's a better way to kind of do this, which is basically instead of grouping, to look at the cumulative distribution of the predictions, and compare that to the cumulative distribution of the label. If you compare the cumulative distributions of both, then you don't have this grouping issue, this binning issue. In our software package, we still also make plots like this, and the main reason that we make plots like this is because it still makes nice visualizations. So it still has this grouping, and for each of those, we can for each group, we can show you not just where the mean is, but we can basically compute the confidence intervals on that group as well. So this is how we show this in the software package. And then I'll show this when we get to the notebook. So this method that we just mentioned with the cumulative distributions is called the estimated cumulative calibration error. It's also nice because it can basically give you like a p-value and a statistical interpretation for like, okay, what's basically a p-value for the null hypothesis of being perfectly calibrated. So this gives you some statistical, basically now you can basically draw conclusions both on statistical evidence of whether you are miscalibrated, as well as kind of effect size. So both significance and effect size of like miscalibration you can estimate here. And because we are estimating it for many groups, what we can do is we can actually make a plot like this. This is one of the kind of visualizations that we have in our software library. So we have, you can calculate this. This is just one data set where actually every dot here is a subgroup that's been created out of your data set based on your features. So you see here the smallest ones, you see here bigger ones, and because the trivial subset you can create out of your data is just the whole data. You don't slice on anything, right? So you can see that this data set is like, well, this is the size. So I don't know, like 300,000 samples in the test set or something like that. And you see that on the y-axis we have the ECCE value. We can calculate the ECCE basically in two ways. We have an effect size metric for it, and we have a statistical evidence metric on it. And that second one you can express either in a p-value or in sigmas, which is basically the number of standard deviations from being perfectly calibrated. So if this is high, you basically have a lot of, you can think about it as like if this is high, you have a lot of evidence that this group is miscalibrated. If it's low, then you don't. Statistical significance is like around, it's like normally with a normal distribution, you kind of used to things being statistically significant if you're like above a sigma of like 1.96, typically used to. But this distribution here is not the normal distribution. So the threshold for statistical significance is not at 1.96. It's actually at, I believe it's around 2.5 or something like that. So you see here in this particular example, the model is like very miscalibrated, like 45 sigmas. And you see other smaller subsets are kind of have other sigmas. Small segments, like whenever we slice into really fine-grained small subgroups, the sigma was really small, but to be honest, this is more of a small sample issue. We just don't have the statistical power to detect miscalibration in such small groups, right? So that doesn't mean that they're not miscalibrated. It just means we don't have the sample. We don't have enough sample to say basically if there's are miscalibrated or not. And some of you might know a method like isotonic regression. Like the two most well-known methods for probability calibration are called plot scaling and isotonic regression. So these are kind of famous methods. I just put on the slide here what happens if you apply isotonic regression to a data set that's kind of has these calibration issues. And it's actually nice what you see happening here. So here, this was the whole data set, right? It's very miscalibrated. Now we apply isotonic regression and the whole data set drops from here to here. So we fixed calibration, right? This is typically what you look at and you're kind of measuring calibration on your whole data set. But look at what happened to all these subsets, right? All of this here still miscalibrated, right? So we fixed calibration globally. We didn't fix it in subsets. So this is kind of just an example of what we see happening, and kind of showing just demonstrating that applying any kind of standard calibration technique doesn't solve the issues that we showed at the beginning. So let's go back to the notebook. So previously I ran everything up to making the dataset split. Now we have a section where we just train a very simple model on this dataset. So in this case, it's just some basic scikit-learn pipeline, doing a little bit of like data pre-processing and then applying a logistic regression. It's like very simple, basic stuff. So we run that, and we fit our logistic regression model on this data set. It's a logistic regression, so it shouldn't take too long. And then after that, we are it on training? Yeah, it's on training. Okay, so now we can basically just do some basic check on the test set. So okay, did this model do a reasonable fit? So yeah, we see like area on the receiver operator curve, like 0.88. We got log loss, 0.42. So okay, seems at least to be getting some. At least seems to be getting some signal. It's not a completely random noise we're generating here. So now we can basically one of the plots we have in our library is this plot global calibration curve. It generates the plot I showed you on the slide earlier. So basically, now you can see that, okay, so here in the back we see how much data is in the different buckets, right? So what we see is...
This is a building announcement.
This is the fire alarm.
The fire alarm system is about to be tested. No action is required.
Is it just one?
This
So
is a building announcement.
we get more of them.
The fire alarm system is about to be tested. No action is required.
Is it 2 or is it doing another one? It might be done. So here in the background you see basically the... Oh, okay.
Attention please. This is an emergency. This part of the building is being evacuated. Please leave the building immediately by the nearest exit. Do not use the lifts. Attention please. This is an emergency. This part of the building is being evacuated. Please leave the building immediately by the nearest exit. Do not use the lifts. Attention please. This is an emergency.
Okay, let's hope that's it. Right, so here in the back we see that the...
This is a building announcement. Testing of the fire alarm is now complete.
Okay.
Please respond to any further alarms. This is a building announcement. Testing of the fire alarm is now complete. Please respond to any further alarms.
All right, that's it seems. So here in the back we see the distribution of the data. So we see most of our predictions are kind of between 0 and 0 dot, I don't know, something very low. For each group we can see what was actually the average of the label. So in this case here, in this group, and for each of those we can also show like whether it's kind of significantly miscalibrated, and these are shown in red, or whether they are not significantly miscalibrated. So this is kind of with the standard binning scheme of the ECE, so we just kind of slice up the data in equal kind of slices on the probability space. We also have this other way of kind of making the binning, which I find typically pretty useful, which is, let me see, what's our API again? We can do this binning method, and we can set it to equisized rather than the default is equispaced, which is how expected calibration error tends to make the bins, which is just like equally large buckets on the probability space. You can also say like, okay, now we actually want to use kind of quantiles for the binning, and we want to basically just make sure that we have equal number of data in each bin, and that kind of makes the chart a little bit funky because you're kind of what you see now is that basically your confidence intervals, like all these measurement points, they kind of jump around a little bit. Like we see lots of them like suddenly here, right? Because this is where most of our data was. So it makes, in that sense, makes the chart seem a little bit seem a little bit weird, but at least now we have we're minimizing the size of our confidence intervals, right? Because we kind of have like spread out the data equally. We can calculate, we have this metrics.ECCE, which is the metric I just explained. So from this we can calculate the number of sigmas, which is we basically get from which you basically get with this, like metrics.ECCE sigmas. And so that's basically gives you a statistical estimate of like how miscalibrated are our predictions, expressed in number of standard deviations. And we have like a effect size kind of estimate here of miscalibration, because calibration, if you have a large enough data set, your miscalibration might be statistically significant, so you can kind of statistically show it's there, but it doesn't mean it's a large kind of miscalibration, right? It can still be a small miscalibration. Or you can have the opposite. You may have like a large miscalibration in magnitude, but on the small sample you might not be able to it might not be statistically significant, which is why it's typically kind of useful to look at both. So this is how you can kind of compute both. You can do the ECCE, which is the effect size, and you can get the sigmas, which is the statistical evidence of it. So here we get 8.7 sigmas on this particular data set, which is pretty high, right? It's like we're statistically significant if it is like above 2.5 on this particular distribution. So we're going to do an isotonic regression. And then after isotonic regression, we get this, right? So this looks nice. Most buckets are most bins are calibrated and are blue, which means that the confidence interval overlaps with like the nice diagonal line. We see a few of them having miscalibrated, statistically significant miscalibrations, but if we're going to make this many buckets, then and we kind of have a significance level of 0 to 0.5, it's going to be expected that you may have like a few red ones. And okay, we see that if we calculate the ECCE on the whole data set after isotonic regression, we get 1.9 sigmas. So this is no longer miscalibrate, or we no longer have statistically significant evidence for miscalibration after applying isotonic regression, which is nice. But now we may look at let me collapse this thing again. Now we may slice the data by gender. So now we have like female, male. So okay, we were like calibrated on all the data, but now actually we see that this is not calibrated. Like here we kind of, on this whole range, we're kind of underestimating the probability. This is just some public data set, by the way. This is not Facebook data. This is just some UCI data set. And here, for male, we're kind of overestimating the probabilities in this range. So okay, so we slice by one feature, and we're no longer calibrated. And we also see that. So okay, we have 10.7 sigmas of miscalibration for male, and we actually have 9 for female. So this is, and we can calculate the multi-calibration error, which is the metric that we computed. It basically, with the V defined, it basically computes your ECCE on all those subsegments. And we actually take a maximum of those. So not an average, we take a maximum of the sigmas. And the reason is that if you look at how multi-calibration is defined in the academic literature, it's basically defined as what's the worst miscalibration what's the worst miscalibrated segment? So kind of basically defined as the maximum. That's the definition of multi-calibration. So this is in line with the academic definition of multi-calibration, but also it basically just gives us, it makes the metric very interpretable, because now if the tool says like, oh, we have a multi-calibration error of like 9 sigmas, and I want to know why. Why do we have 9 sigmas? You can just, it's a max, so you can just literally look up in the data, like, okay, which segment was so miscalibrated? Which segment cost us, which segment was responsible for the max being 9, and you can just kind of drill down on that particular segment and look at what's going on there, and it kind of makes it easy to diagnose. So in this particular case, we see that, okay, we now calculated multi-calibration error by calling it like this, and we did it on the predictions that we had of the original like logistic regression model, as well as on the isotonic regression post-processing of the logistic regression model. And what do we get? We actually see that isotonic regression, it kind of solved our miscalibration, because we had on the whole data set, our sigmas went down to 1.9, right? So it was no longer miscalibrated. But actually the worst segment, it got worse, right? Our multi-calibration error went from 36 to like 37 to, so actually, you know, we definitely didn't fix like multi-calibration error. Okay, and then we have these kind of plots, which are typically very insightful. Let me zoom in a little bit. So on these plots, I can hover over it and I can really look at, okay, which segment is this? Which segment are we looking at? So completely at the right, this is the largest segment. So this is the whole data set, like not kind of sliced down. And we see here, we had like 8.7 sigmas, which was the number, which was basically our calibration error before of the logistic regression model as well. Then we applied isotonic regression, and we got this 1.9 which had this 1.9 sigmas. So here, you know, you can see those two in the plot as well. If you just take your two rightmost dots, those will just contain the values for your calibration error. But you also see that, you know, this particular segment here is what is particularly miscalibrated. And then I don't know exactly how the features were encoded here. So sex1, I don't know which gender that is, but we can look it up in our kind of categorical feature encoding that we used. But we see that this like gender 1, HP1, that segment was particularly bad, right? So this kind of allows us to diagnose why were we miscalibrated, and this also shows our MCE, right? So the MCE value was just 36.6 something originally, and then after isotonic regression, it was this 37.5 almost. So this is, you know, the MCE values are just the maximum, so they're just these two values basically. So this plot basically gives you a pretty insightful overview, I think, of like what's going on in your data set, where are you miscalibrated, which kind of feature values tend to be miscalibrated. All right, so how do we fix it, right? So we talked only about measurement and the definition and the application so far, but how do we fix it? So multi-calibration, actually the academic literature has been around since like the late, sorry, go ahead. Yeah? Right. Yeah, it's a good question. This actually tends to be less of an issue because of the taking the maximum of the sigmas rather than on the effect size. What we also can do in this, so what you also, so if you have a really small, if you have a really small segment, then you're very unlikely to find like statistical evidence there, right? Because if you have a small sample size, it's very hard to, like your minimal detectable effect will be very high, right? So you tend to kind of find lower sigmas there. It's actually what you see on the plot here as well, right? You see, as the segment size goes up, our sigmas go up a little bit. Like, it's not perfect. Like, there are still outliers that are kind of not the biggest one, like that are kind of worse calibrated than the whole data set. But you know, on the small sample, it's hard to find statistical significance. Right? If we would have defined this on the effect size rather than on the statistical significance, on the statistical evidence, then we would have had that issue much more. So we've had, so that's actually quite many years of like multi-calibration research. It started with like an initial paper in 2018, where the first paper to kind of study this problem of multi-calibration, which is an ICML paper. They introduced an algorithm that's now often kind of referred to in the literature as HKRR. And then there's, 2021, 3 years later, there was the first kind of software library that ended up getting some adoption. It's actually not in Python, but it's kind of an R package called MCBoost. And there have been kind of every kind of NeurIPS and ICML, you see a bunch of papers, and it's growing. So it's kind of a growing kind of research area. But we hadn't really seen it being adopted in industry much. We hadn't really seen many companies actually using any multi-calibration methods. We basically started thinking a bit about, okay, why is this? Why is this kind of, because this, there are all these theoretically nice properties, so what's blocking? What's blocking us from using this? And so I think there were kind of 3 main issues with like existing multi-calibration algorithms that kind of were kind of making it hard to adopt, or kind of making not so appealing. And the first one is that it really required to kind of manually define your segments. So it was not enough to say, oh, I have this age feature and I have this country feature. I want to be multi-calibrated on those. Now you really needed to, like all these existing methods, all these existing multi-calibration algorithms really needed you to manually specify the group. So you needed to say, hey, it's really important for me to be calibrated on Italian teenagers using Android, like really specifically like on that level, not just the feature, but also the value of it, right? And then with this algorithm, you could say, like, okay, I have a set of these groups, like maybe like 10, 20 groups, and I want to be calibrated on all of these, 10, 20. But, realistically, who's gonna, which machine learning engineers really have like intuition for like, okay, what groups do I care about to kind of protect, to kind of, make calibrated? How do we even start thinking about which groups to care about? So this is like a difficult question, and it's like, really don't really have good intuition on how to do this. And if these kind of things tend to be difficult, we don't really have a good idea of how to get started. We just tend to not do it, right? Also, existing algorithms, they tended to be, they don't really scale well with the amount of data and the amount of segments. So the computational complexity of those algorithms was just not so, we quickly ran into kind of issues of scale. And then I think a third kind of pretty important one is that sometimes, like many of these algorithms, so we've been also kind of taking HKRR and a couple of these other algorithms from the literature. We've been applying them on some data sets, and what we've seen quite often is that we can measure multi-calibration error, and it improves. But it comes very often, it comes at the cost of like area under the precision recall curve, or it comes at the cost of like area under the ROC curve, or just so if it, you know, if the traditional kind of metrics that we are kind of typically focused on optimizing, if these kind of, if we're harming those, it's pretty hard sell, right? It's not so appealing to kind of go to some machine learning engineer and say, hey, do you want to use this model that harms your recall? Like, probably no, right? So I think these were kind of the three most blockers. So what we tried to do in this like project is we were thinking of like, hey, can we design a method that doesn't have that does multi-calibration, but it doesn't have any of these, right? We wanna not define segments manually, so we just want to be able to say like, hey, these are our features. Done. We don't want to say focus on Android users that are like teenagers using Android. But we just want to say, like, hey, this is a gender feature, this is a country feature, this is a type of device feature. If there are any segments in here that are miscalibrated, then find them and fix them. One that's more scalable, and we want to like safeguard against degradations in like the traditional kind of metrics that we're used to looking into in machine learning. So this is the paper. It's called MCGrad, Multicalibration Gradient Boosting. Multicalibration gradient boosting is the method. MCGrad, Multicalibration of web scale is the name of the paper. We're presenting this at KDD this year. So what we're doing here, actually, let me first run through a few cells here and then go back to the slides, just so that we don't have to wait for the fit while later on. So here I'm just calling, I'm just creating the MCBoost object. I'm calling fit, it is now fitting. So what are the key ideas of the paper? The key ideas is like basically, okay, it's actually there exist already kind of, you know, decision tree algorithms. And what do decision tree algorithms do? Okay, they take your features, they slice your feature space in particular ways, and basically each node in the decision tree is basically again a subset of data, right? So here you have all your data, that's the root node. Then you split, and it's split on device. So okay, here you have the data set of mobile users, right? And here you have the data set of desktop users. Then a decision tree can basically do this recursively, so you can split again. So here you have a data set of mobile users in the UK, right? So we thought, okay, if we want to get rid of manually having to specify all these subgroups and just giving it the features, then actually there are some interesting ideas in this kind of decision tree, area, because they already kind of do some splitting and finding. So what we want to do here is that the main idea is that if there exists a certain area of predictions that in a particular kind of subset of the data, for example, like mobile users in the UK, if there exists like a interval of the predictions here that is miscalibrated, then correcting that must be likelihood positive, right? It must bring down your log loss. There's no other way. It has to. It's like, I mean, you can also prove this, but so if this is the case, then okay, maybe it's actually pretty easy. Maybe we actually just need to do a decision tree where, in addition to the where basically we learn on the root nodes to kind of add a little bit to your prediction or kind of reduce a little bit the prediction just to kind of maybe we need to add a decision tree that kind of learns to do corrections to your initial prediction that you got out of your initial model, and that kind of just are like additive predictions. But if these can be local, right? So here we see this part needs some particular correction because we were too low. In this part we were predicting too high. So clearly these corrections are kind of they are dependent also on the prediction we initially had, right? So if we're kind of doing this splitting, then clearly also the prediction itself needs to be something that we can can also split on. So the decision tree needs to have that as feature as well as your initial features. But now there can be multiple groups at once, right? So one group can be miscalibrated, but another one might also be. And the idea is that, okay, we need this kind of we needed to do this kind of additive corrections to the prediction. Well, there already exist kind of 3 algorithms that do that, right? That take your initial prediction and then find kind of additive corrections in particular subgroups, and then do not just one step of that, but like after one step of additive corrections, find another kind of set of groups where you kind of have maybe become, or your predictions maybe have kind of gotten worse because of the first ones, and you kind of refine and refine. And these are gradient boosted trees, right? They already do this. And gradient boosted tree algorithms, they allow you to kind of like the well-known public kind of gradient boosted decision tree packages like XGBoost, like GBM, and so forth. They actually allow you to specify the initial prediction from which you're kind of making adjustments. If you don't pass it, like it's a kind of a parameter that these packages allow for. If you don't set it to anything, it just takes the mean of your label on your train set. So you're just kind of boosting from the mean. But you can, if you prefer not to, you can boost from some other set of predictions. So if we're kind of calibrating, using this for calibration, we can just say, okay, this is the predictions we got from the uncalibrated model, the initial model that we're calibrating. So we set the initial predictions to that, and then we find additive corrections relative to those scores. All right, this seems really simple, right? It's like so far it sounds like, okay, we're just using GBDTs, and are we done then? It's like, not really. So okay, what we're getting is that we may start off with some kind of logits, which are the logits we're getting from the model that we trained. Then each GBDT step basically may learn a split like this. So we can have device and country, and then we can also split on the prediction itself I mentioned. So you can say, okay, if the logit is like larger than this, then maybe we've been predicting too high, so we need to subtract a little bit of the logit. Or if we were too high, or if we'd be below this, we were kind of predicting too low, so we need to add a little bit to the logit. So you may learn things like this. However, this doesn't quite bring us multi-calibration. It gets us, if you like do a gradient boosted decision tree like this, it gets us somewhat close to multi-calibration, but it doesn't quite do it. And the reason is, all the time that you're doing these additions, this logit feature is the same, right? Like this logit feature is just, like you have a fixed feature set in gradient boosted trees. Like whenever you call lightGBM, you define the features once and that's it. Well, here we don't quite want that because we want to be able to split on the features. But we've kind of, it's kind of a special feature in some sense, because after we made a correction, in some sense, we've kind of defined that as a new feature. We basically made a new feature that has new values now, right? So this is the main idea from MCGrad, is that you do some round of kind of gradient boosting, but now we really have a dynamic feature. So as we boost, we have one feature whose values keep changing because it's basically the output of the corrected logits of the previous round. So it's kind of one kind of twist to it that you kind of need to make gradient boosted trees do this multi-calibration. And how to get this scalable? Well, there are already like software packages that kind of implement gradient boosted decision trees in quite scalable ways. We implemented this on top of LightGBM. Also, there are already kind of regularization methods and all kind of things that kind of allow us to avoid overfitting, and we see that this is quite useful to actually avoid this these kind of overfitting issues and degradation in precision recall kind of metrics that we've seen with the other multi-calibration approaches. Yeah, so this is what we're typically seeing when we apply MCGrad, is that after we do an MCGrad kind of post-processing, we typically are kind of, all the predictions are kind of nicely at the bottom, and not only like where isotonic regression kind of calibrates your whole thing, but not all the subsets. With MCGrad, we typically see results like this, which look much nicer. All right, so in the meantime, this MCGrad thing has fit. We have implemented, so I mentioned that MCGrad actually does multiple rounds of GBDTs, so it's not just one GBDT in some sense. And this is another kind of protection mechanism for against overfitting that we implemented. So we basically have some early stopping. We did one round of this multi-calibration boosting, then a second round, third, fourth, fifth, and here we actually saw that the log loss on the test set started going up. So basically here we stopped, and these were just the kind of on the holdout set. So yeah, now we can look again at the calibration curves for males and females, with previously after isotonic regression didn't look great yet. Now they look much better. So sigmas of 2.5 or below are like lack of statistical evidence of miscalibration. We didn't quite get there. There's still some statistical evidence of miscalibration here for the male group. Not anymore for the female group, but you know, we got pretty close to it, because this is still very, very close to the threshold of statistical evidence. We have this metrics of multi-calibration error, so we can kind of compute this. And this is the plot I just showed you on the slide on this particular data set. All right, so now at Meta, we wanted to evaluate this at scale. So we wanted to know, does this actually work, right? There's one frequent machine learning model training. There's one machine learning model training platform that's used quite a bit in the company, where we integrated this MCGrad approach into a sense that, in a way that every time any machine learning engineer trains a machine learning model on this machine learning model training platform and runs a training and evaluation job, we clone this training job. We calibrate the model using MCGrad, and we run the exact same evaluation procedure. So on the same test set, we calculate the same metrics as the base job that we cloned. There's like, I don't know, a couple of thousands of machine learning model training jobs being submitted to this platform. Hundreds of different kind of models that are deployed somewhere in production. So we were able to get a nice kind of set of results from this. We noticed that, you know, for different metrics, so we were able to validate, did we actually succeed in improving this kind of different metrics, and did we achieve the goal of kind of avoiding degradations in like PR curves and recall, and because that was one of our design criteria, right? So we see, well, mostly, not always, we see that in like 80 to 90% of the cases, we actually improve these metrics. In the cases where we didn't improve, typically they were basically the same. There were some like small percentage of like 5% of cases where it did really seems like we were still harming log loss of area under precision recall curve. We did some case studies into a bunch of those because we wanted to know what's going on and is there anything we can learn about maybe further improving our algorithm. What we actually saw is that those, basically without exceptions, were all like errors in machine learning engineers setting up the training job, where, for example, they applied weighting of their samples at training time, but they didn't apply the same weighting at test times. So, you can't expect to kind of get a reasonable evaluation out of such kind of statics. We applied this also to a set of like UCI data sets, and this was kind of more for the purpose of the paper that we published at KDD. So we compared against two methods from the literature, HKR and this a more recent one, it's called DFMC, as well as against regular calibration approaches like isotonic regression. And we measured kind of our own multi-calibration error metric, as well as this ECCE, log loss area precision recall curve. And we see basically, we have the rank here of if you sort on each of these 11 data sets, you sort the metrics, you sort the methods according to which does best on this metric. Then you see we basically almost always have the best multi-calibration error, which makes sense because this method is intended to do that, but also DFMC, HKR, which are kind of also multi-calibration methods, they're kind of not really achieving it, and funnily enough, even doing less well than isotonic regression. Always best in log loss, average area under precision recall curve. If you just want to be calibrated globally, so you don't care about subsegments, but just calibrating on your whole data set, then you see that you're typically still a little bit better off to do isotonic regression, which makes sense because it's intended to calibrate globally, while our method is not. It still does decently on that. A couple of individual data sets. Yeah, so this is basically the summary of it. It's like multi-calibration is a stronger property than calibration. Goes far beyond that, and I hope I convince you that this is a property that also matters in like production systems. I showed this MCE metric, which is simple to interpret because it's just a maximum. It has like nice statistical properties. Achieves low MCE. I showed MCGrad, which achieves low MCE. It's funny, I still have, will be open source in the future, but it's, we've just seen it. It is open source now. Yeah, I hope you all will try out MCGrad on your data sets. And if you have any feedback or ideas, then please reach out. You can reach me on niek@meta.com. We still have like 10 to 5 minutes left if there's any questions. Or if you just want to try it out on your own data set and kind of, yeah.
Do you find the need to do like feature engineering for the calibration? Because like for example, like some feature they have like very high cardinality and uneven distribution with
Yeah.
like every part of components. So if you like use country as a feature with like EDF versus angle, they have a very different like calibration error, and
Yeah.
you have to like sometimes group it to use better performance.
So what we did in this study, where we integrated it into this machine learning model training platform, is we don't change anything. So the features that MCGrad gets is just the same features that went into the original model. So we didn't do anything here, and we still got these results. There's actually, I didn't touch upon this much in this presentation, but there's, if you look at the AI fairness literature, and this kind of conferences like FACT and this kind of conferences that kind of study fairness in AI, there's more and more papers in that field coming out that basically claim that multi-calibration is fairness, and to be fair, you need to be multi-calibrated. So from that perspective, I would say that if you believe in multi-calibration as a fairness notion, and you want to achieve fairness with respect to a particular feature, or with a particular dimension, then that's the feature you need, right? So to think about this from a feature engineering point of view, you may, you could always try that just for the sake of, if you want to do that for the sake of trying to improve your model, you can do that, as you can do with any kind of machine learning method. But if you want to do that, but if there's a particular feature that you care about being fair with respect to, like, I don't know, we've seen gender a couple of times in this, in this presentation, then that's a very natural feature to put into MCGrad.
Iterations previous or three, so that's a way of rolling back.
Right.
But I think once you update, you may find, I think you mentioned certain segments, maybe that were performing well, may then perform worse in the next step.
That's good. That's a good question. I remember we tried it at some point. Okay. Because also we weren't sure. I don't quite remember what we were seeing, but I think it didn't make much of a difference. So we decided to kind of just simplify and like not to kind of add any bells and whistles for which we didn't have any strong evidence that it helped.
Okay,
We have 5 minutes left. So if there are any more questions, I'm happy to take more. Yeah.
For the presentation, I wanted to ask, like, we discussed calibration among classification problems. Like, have you also spent some time, for example, on the regression problems, or like how this method could be also applied in regression?
Yeah, that's interesting. We have a regression version of this developed internally. We haven't published about it yet or open sourced that part of it yet. That might come. But yes, there are things that can be done. Yeah.